morning, everybody, or rather good afternoon to those of you in Europe. So I wanted just to quickly give you some of the standard messages first, and then we are going to have a small repetition of what we did last week, and then we're going to jump into today's topic. So if you now scroll down on the standard GitHub page for the course here, what we had last week was a discussion on entanglement and a little bit further discussion on density matrices and measurements. And we derived also this Schmidt decomposition, which is a useful quantity when we are going to analyze whether a state is entangled or not. And as usual, you will find the teaching material at these different links. I have some small recommendations from this textbook by Scherer. And you will also find the video and the handwritten notes. And as I mentioned in the previous lectures, not all my notes for the present days, which we have, are typed in. So that means that the handwritten notes are those which, or the whiteboard notes, are the notes which you can use together with the video till I have typed up my lecture notes. And the lecture notes today, they are going to focus more on entanglement and some actual calculations on how we can define whether state is entangled or not. And then we are going to dive into entropy and density matrices again. So we need to discuss two different types of entropies which are used in quantum mechanical or quantum computation analysis. And one of these is the so-called Shannon entropy, which is the classical entropy. And then we have the quantum mechanical variant, which is called the von Neumann entropy. And these are quantities which are tightly related to the density matrices. If we get some time, we will look at these Einstein, Podolsky, Rosen, and Bell's inequalities, but we may skip that topic. Next week, on the other hand, then we are going to, after all these preliminaries, because what we basically have done now is to go through some basic definitions of quantities. And then we are going to more look at some simple quantum algorithms and also look at the quantum Fourier transforms. And if we get time, we will start looking at the algorithms for finding the eigenvalues of a quantum mechanical system. And the quantum mechanical system which we're going to introduce then is a system which will define more or less what we will do in the first project. So this first project is not fully defined yet, and that is essentially because we need to go through some formalism first. So I hope you can bear with me in this connection till we have gone through some of the basic formalism for solving quantum mechanical problems. So that means that we need at least 2 more sessions before we've gone through some of the basic formalism which is needed. Okay, so if we go back a little bit to what we did last week, so let me quickly remind you of that before we dive into today's material, which is actually more about entanglement and also about the density matrices, how we can use them to define whether a system is entangled or not, what we mean by a pure state, and what kind of measures we can use in order to say something about entanglement of a system. So these are important things, and we will relate them to a simple Hamiltonian problem, which we also mentioned last week. But let me bring back some of the definitions which we introduced last week. So last week we discussed more entanglement and density matrices, and we are going to continue a little bit with that. And one of the systems which we will stay with in order to illustrate many of these concepts is a system which we call a bipartite system, or just a 2-qubit system. And in that case, we were looking at qubits in system A and B. You could think of this as 2 ion traps, where you have 1 ion in each trap, or you can think of these as confined electrons, which move in harmonic oscillator-like traps. And they can be thought of as almost independent systems. Ideally, one would like to think of them as independent systems, but a real world system, in a real world system, there will always be quantum mechanical correlations. And so the degree of independence is something which is also worth discussing a little bit later. We are going to assume now that these systems have only two states. In real life, the systems have an infinity of states, but we are going to assume that each system has, each subsystem has a state 0 and a state 1, which we then indicate by these spinors here. And then we can make a tensor product of the two systems. And that means that we do the tensor product of state 0 in system A and state 0 in system B. And this is often in a sloppy way, written just like this state which you see here, 0, 0. And this is simply given by the augmented vector now. So you went from a 2 by 1 vector and you go to a, actually this is a 1 by 2 vector. If you take the transpose as a 2 by 1, then you end up with a vector of dimension of length 4. And same with the different states here, 1, 0. Actually, this should be interchanged. So this would be 0, 1, and this should be 1, 0. So have still some typos here. Then what we did was to define linear combinations of these states. So these are so-called, the first ones are just product states. And it's easy to see that these product states, which we have here, 0, 0, 0, 1, 1, 0, and 1, 1, they form an orthonormal basis. Now, you can form another type of orthonormal basis, which we introduced last time, and we use that basis to define entanglement. And this is now given as a linear combination of these orthogonal states which we have here. So these so-called Bell states, they define a new type of orthogonal basis. And you could now think of having these 4 states as your new basis state. Now we are coming back to these specific states a little bit later, and we are introducing them now because we use them as definition of entanglement. And you can measure one of the qubits of one of the above states, and that automatically determines, as we saw last time, the state of the second qubit. And to convince yourself about that, you can just perform a measurement where you project out one of these. And this is now given by the tensor product of just the identity matrix for system B. We're not doing anything with system B, and we're simply projecting out the qubit 0 for system A. And similarly, we could make a measurement where we project out qubit 1 for system A, and we just leave system B unaffected. And the matrices which you get then, since these are tensor products, then they become 4 by 4 matrices, as you can see here. And when you perform the operations then, and you project out one of these qubits, what happens then is that you get a probability of a half, as expected. And then you can look at the state after the measurement, and this is the quantity which we are often interested in particular, later, when we are going to look at how to extract the eigenvalues and eigenvectors of a specific system after a measurement, then what we see in this specific case is that the state after the measurement. So what you could think of now is that you perform a measurement on one of the qubits, and that specific measurement leaves you in a new state after the measurement has been done. And in that specific state, what has happened is that we have projected out a specific part of this Bell state, which was a linear combination of the 0, 0 and 1, 1. And what happens then is that this specific state here, you see from the last two equations that the state of the second qubit is actually determined, even though the measurement has only taken place locally on system A. So you could think of acting on system A with a laser, and system A is basically independent of system B. So you could think of having localized particles within the uncertainty principle, which are particles where you can perform measurements on without affecting the other system. And when we do that, we can actually say that the other system, with pretty high precision, that the other system is in qubit 0 when we perform this type of measurement. When we measure qubit 0 in system A, we know exactly that system B is also in qubit 0. And then if we perform a measurement on qubit 1, the other state, in the system A, we know exactly what kind of system it is in that one. And this is something which we used also to define what entanglement. So this Bell state is an example of an entangled state. And that means that we cannot write it as a product of specific simpler states. And that means that when we have this, the state is composed of like this Bell state here. So it's a kind of mixed state, and we cannot determine in this case whether system A is in state 0 or state 1. So system A is in a linear superposition of 0 and 1, and same with system B. And it is not possible to determine individual states of system A and system B respectively. And that's when we say that the system is entangled. Another example which many of you may have encountered in courses in quantum mechanics is, for instance, a simple system which could be the ground state of the helium atom, where you have 2 electrons in the 1s state. And in addition, you would have the spin degrees of freedom, where spin is equal to 1/2, and it has projections either spin down or spin up, which have values -1/2 and +1/2. And we typically label these as spin up and spin down states. These, the single particle states, you could now think of electron 1 being system A and electron 2 being system B. This is actually not a very good usage of what we might call separate systems, because it belongs to the same system. But in that case as well, the total wave function, when you make an ansatz for it in terms of these single particle states, is actually a system which cannot be written out as a product of just these single particle states. It's actually a linear combination. And this would also be an example of a state which we would call an entangled state. Now, today we are going to look a little bit more into measures about entanglement. And typically a state like this one is also a state which is well defined. We know that the system is in this state, and we normally call that a pure state. And as you will see with a pure state, the trace of the density matrix is equal to 1, the square of the density matrix. And later we are going to use the density matrix to define what we mean with a mixed state and a pure state, an entangled state and a not entangled state. We can also define the so-called Schmidt decomposition, which we went through last time. And this is also a very useful way to measure whether we have an entangled state or not. Now, the topic which we ended with last week is the so-called density matrix with a simple Hamiltonian. And this is a system which we're going to pick up today, but we need to go through some further technicalities with the density matrices and entropy. So if you look at today's topics, we are going to have, after this review of the Schmidt decomposition and entanglement from last week, we are going to look at more on entanglement and density matrices, and then we are going to jump into entropy and the definition of entropy. So now it's time to switch over to the whiteboard notes. And then we are coming back to this simple system, which we introduced last week. And we're going to look at that one as a way to gain some insight about the density matrices, entanglement, and many of these other quantities which will define the way we analyze a quantum mechanical system. So entangled states are very important. And you saw with these Bell states, by making a measurement, projecting out one of the states, we can actually say something about the other state. And these are things which are going to be pretty important for us when we're going to analyze the quantum mechanical states and build up quantum gates and quantum circuits and perform calculations of, let's say, the eigenvalues of a Hamiltonian system, which is going to be more the focus in this course here, and the focus for the first project, or perhaps just the final project. Okay, so I'm going to switch back to the whiteboard, and let me just bring that up. So we need to look at some practicalities about entanglement before we go over to this topic of entropies, which is a topic which will allow us to make statements about whether a state is entangled or not. And it's also, in classical computing, it's an extremely useful quantity because it tells us about how we can encode information and what is the most efficient way to encode information here. But let's now remind ourselves about some technicalities which we will find useful here. So one of the things which we looked at was the spectral decomposition of a specific operator. So just a small moment. It seems that my pen is actually not working. Just a small moment. I just need to get a boost of my pen here. There's always some kind of small technicalities which are needed when you are using these whiteboards. Okay. So one of the quantities which we looked at 2 weeks ago was the spectral decomposition of an operator. And this spectral decomposition of an operator A, and I will try to keep this hat symbol, this has a sum over all the possible states, and they were defined by this quantity A, which are the eigenvalues of these operators, given by the projection operator. So A could now be an eigenbasis of this operator A. So this is the so-called spectral decomposition of a given operator. And we can perform operations. So you could think of having a function of this operator A. The simplest possible function is actually have repeated actions of the operator A. And this is simply going to be given as a sum over all the states which we have. And then this function of this operator A, and this is acting on the projection. So remember now that this quantity which you see here is actually the so-called projection operator. And that projects out a specific state A. Another quantity which is important for us is about the trace. And the trace has some specific properties. So if I take the trace of three matrices A, B, C, we know that this trace is actually given by this kind of simple cyclic permutations. And this is going to be very useful now when we are going to look at a unitary transformation of, let's say, the density matrix. We can rewrite this as C times B of A. We have an outer product formulation, which is also very important for us. And we proved that last time. Not last time, but the time before. So we have the trace of A acting on a specific projection of psi here. And this can be written out as psi of A of psi. And we have also defined the so-called density matrix in terms of these projections. And the density matrix rho is now given by the sum over all the possible states which we have. And this is now given by some probability P of I, which is the one of the eigenvalues of the density matrix of psi of I. This is also called a density operator. And this quantity, if we now perform a transformation, where we let psi be transformed by a unitary operation of psi of I. And we know that this is a unitary transformation which has the properties that if we multiply it with the self-adjoint, this is just equal to the identity matrix. Now what happens is also that the trace of the density matrix, rho, is equal to 1. This is a quantity which we showed 2 weeks ago. It means that when we perform a unitary transformation, this trace is actually conserved. And you can easily see that because if we now look at this rho multiplied with U and multiplied with this self-adjoint, This is the same as I of P of I. And then I would have the matrix U of psi of I. And then I have my psi of I multiplied with U, like this. And the important thing now for us is that the trace here, which we have, is when we take the trace of this specific quantity, since these are free matrices now, we would have the matrix U, the matrix rho, and the matrix of the self-adjoint. So that is something which I can rewrite as trace of U of times rho. And we know that this is given by the identity matrix, and the trace of that one multiplied with another matrix is just the matrix itself. So this is the same as trace of rho, which is actually equal to 1. And this means that the trace itself under unitary transformation is actually a conserved property. So let's go back to more definitions of the density matrix. So if we now let this density matrix be the density matrix of a system A and B, so what we could do now is to let, and one of the things which we are going to do now is to project out the density matrix of either system A and system B based on the density matrix of a composite system. So what we're going to do now is we're going to let this A be. This is going to be the density matrix. A density matrix of a composite system. In our case, this is a bipartite system, but we can, there's nothing which hinders us of making this a more complex system. So in our case, we have picked the system A and system B, and this is now a density matrix, a bipartite system, which is spanned by two Hilbert spaces, given by the tensor product of the Hilbert space A with a Hilbert space B. So we are still thinking of these as independent systems. They are not necessarily that. And what we could also say is that the state I of B is an orthogonal basis for the system B. So is an ONB. So ONB is this acronym for orthogonal normalized basis for this system B, and you can assume that there is a similar basis for system A. So what we are interested in now is to define something which is called the partial trace. So the partial trace, because now we want the density matrix, so we're going to project out system B so that we're only left with system A based on system AB. And the reason why we want to do this is that we want to say something about system A based on the total system. So we are projecting out the density matrix for the subsystem, and we are going to define measures for whether the subsystem is entangled or not. This is going to have consequences for us, because if the system A, the subsystem, is not entangled, which means that it is in a pure state, then the system is exactly defined and we know exactly in which state the subsystem is. If the system is in a mixed state, then we cannot say exactly in which of these basis state the system is. And this has important consequences when we now are going to discuss entanglement in systems. So let's now, and there are some topics here which we need to just have a better understanding of, but let's go through some technical definitions first. So the partial trace over the Hilbert space. So what I'm doing now, which is a standard definition of this partial trace. So we take the partial trace over the system B. That is going to project out the system A is given as, so this is a formal definition. So this is a trace. And I'm going to put a label B here to indicate that we are tracing out the system B out of the bipartite two-level system. No, not two-level system, but a bipartite system which contains system A and system B. And if these are two individual particles, we could think of this as a two-body system. And this is going to be given formally as a projection operator, which is now going to be defined as follows. So I will have a sum over I, and these are the states in system B. And this is now going to be the product of an identity matrix for system A. And then I have my sum over this orthogonal basis here. So I'm producing now a matrix, and this is multiplied with the row of AB. So this is my density matrix, which I have defined. And then this is again multiplied with the identity matrix for system A with a tensor product of this basis B. So we're assuming that there's an orthogonal basis, an orthonormal basis. And this orthonormal basis is a basis which I will now use to project out system B by taking this trace or the partial trace. And this system here produces a state uses a new density matrix, rho, which is given by this trace of B of the original density matrix, AB, of the many-body density matrix. And this is called a reduced state. Or what's normally called a marginal of system A. You may remember from courses in statistics the definition of a marginal probability. So marginal probability is if you think of a probability which depends on X and Y, and then you integrate away the Y degrees of freedom, and then you have a probability which is only defined by X. So think of this as suppose now we have the parallel would be a probability for X and Y. And suppose now that this is given by the product of the probability P of X and P of Y. We are assuming that these are independent and identically distributed events. So what I could do then is simply to find that P of X now would be given by Y, which is integrated over the domain of all possible events for Y, of P of X, of P of Y, of dy. And normally these probabilities are normalized. So I have a P of Y of d of Y, which is equal to 1. So that means that in this specific case, P of X is actually equal to P of X. Alternatively, we can have probabilities which are not given by independent and identically distributed variables. And then I would have to perform the integral here. So the probabilities or this kind of definitions which you see here is something which is parallel to the definition of the marginal probability. So this is this subsystem which we have traced out now is normally called a reduced state or just a marginal of system A. So one thing which we will see immediately from a simple example now is that the trace of this marginal probability or subsystem density operator is equal to 1. You will also see that if I perform a similar projection for system B, this is also going to be equal to 1. So this row of A is actually a valid density operator, which has a trace 1, and it's also semi-positive definite. The thing we have to keep in mind is then that if we look at the probabilities which we have, so if we think of a general density matrix that is given by, or density operators given by this projection or series of projection operators multiplied with a probability. And we also have that the sum of these probabilities, they sum up to 1. That's a very important statement. And the trace of the density matrix, as we saw earlier, is also equal to 1 here. So what we're going to do now is just look at an example. So let's go back to this Bell state. And let's try to set up the way we would construct this subsystem. So we have the Bell state, one of these Bell states for the system AB, which we labeled as, or which we wrote as the linear combination of the state 0 for system A and state 0 for system B. And we defined this as an entangled state because the two subsystems, we cannot define in which state these subsystems are in. They are actually in a superposition of the states 0 and 1. So we have 1 of A and the tensor product of 1 of B. And we wrote this in a sloppy way, or in a more compact way, as 1 over square root of 2, and then we had 0, 0 plus 1, 1. So typically when you see states written in this specific way, it means that we are looking at a tensor product. So this is, if you look at this specific system which we have here, this is also, if we think back to the Schmidt decomposition, this is also the Schmidt decomposition with rank D equals 0. So if you think back to last week, this is also the Schmidt decomposition. With Schmidt number or Schmidt rank, D equal 2 here, because we have two specific states. And what we have is two components, which we call lambda 1 and lambda 2 last time, which are just given by 1 over square root of 2 here. So just to remind you of the Schmidt decomposition, we can actually write a state using the singular value decomposition. We can write this as a lambda I of I times I. And in our case, I here is 0, 0, and 1, 1. So the Bell state which we have is actually a Schmidt decomposition. We say it's entangled because the Schmidt number D is larger than 1. And what you also see is that this lambda 1 squared plus lambda 2 squared is equal to 1. And that's also an important requirement here. Now, let's now look at the calculations here. And let's set up the Schmidt matrix and then define how we're going to perform the projection of the subtrace. So if we now look at the matrix which we are going to have when we now set up the density matrix. So let's just define the density matrix for this specific state. So we have a density matrix for the Schmidt, the Bell state. This is going to be given by AB of phi plus. So that's the formal definition of the density matrix. So you have a specific state, and from that state, you can make now a definition of the density matrix. And if you now write out the basis states which we have, this is the same as 1/2. And then I'm going to have 0, 0 with obviously 0, 0. So these are outer products now. And then I have 0, 0 with 1, 1. So that's not necessarily 0. And then I have 1, 1 with 0, 0 plus 1, 1 with 1, 1. And these are outer products. And if I put everything together, I know that the first matrix is simply going to be 1, 0, 0, 0. And then I have zeros for the rest. So that's the projection operator, which comes from this. And we see now that if we act on this on phi plus, this will simply project out the state 0, 0. And then we have the other matrices, and one of them is just going to be 0, 0, 1, and then we get zeros. This is not very exciting actually, but I'm writing out all the possibilities which we have. So the third one gives us now 0, 0, 0, 1. It's actually a useful exercise to do these things, because that tells you how you're going to write a code for setting up the density matrix and also trace out the density matrix of a subsystem. And this gives us the final one, which is 0, 0, 0, 0, 0, 0, 0, 0, and then we have 0, 0, and 1. Exciting, isn't it? And this is then multiplied with a factor of a half, like this. Now, bringing this together now, what we have is a factor of a half. And when we're going to have this matrix, which is 1, 0, 0, 1, and then we have zeros. So you see clearly quantum mechanics is very much applied linear algebra here. Now, what we want now is to trace out, let's say we want to trace out qubit 0 in system A and qubit 1 in system A. So what we're going to do then is to tensor the states 0 and 1 with an identity matrix I, which now represents the system B here. So what we want is the following. So we want to trace out and the qubit 0 and qubit 1, 0 and 1 of system A. So what we are going to do then is simply to perform a tensor product with, so this specific state A here now is now going to be a tensor product of 1, 0 with the identity matrix. So we have 1, 0, 0, 1. And this is now going to be the same as we wrote out as this operation with the identity matrix here for system A. And this is now multiplied with, and if we're putting up this in this specific way, this is actually the tensor product with one of the qubits in system B. And now we have specified just qubit A. No, sorry, qubit 0, which is now given by this specific vector here. If we then set up that one, this is now going to give us, since we have a vector which has a length 2 and a matrix which is 2 by 2, so this is going to give us a matrix of size 4 times 2. So we will get a matrix now, which is 1, 0, 0, 1, 0, 0, 0, 0. So that would be that element. And if I do the same thing with this 1 qubit, that's going to be given by 0, 1, and tensor product with the identity matrix, which is 1, 0, 1. And that's going to give us a new 4 by 2 matrix, but now with the following values here. Then I can go back now and I can perform the total projection. So what I'm going to do now is simply to set up this tracing out. So if I now trace out with respect to system B, the density matrix, which I have for the Bell state plus, phi plus. So I have defined my density matrix for that specific Bell state, which is this one. And now I can trace out system B from that specific case, and then I can get the subsystem A. So what I'm going to do now is to multiply from the left with a transpose of these vectors which you see here. So I'm going to So I'm going to multiply with a transpose of this one, and then I'm going to take the multiply with a matrix, which represents the density matrix of system AB, and then finally I'm going to multiply with this quantity. So that means that what I'm doing now is simply to perform the matrix multiplications, which are going to give me this, where did I put that one? Which is going to give me this trace here. So now what I'm doing is to set up this matrix for 0 and 1 for system B, multiplied or tensor product with the identity matrix for system A. And similarly, I'm going to multiply it with this final matrix here. So this was a 2x4 matrix. This is a 4x2 matrix. And this is a 4x4 matrix. So now I'm just going to perform these matrix multiplications. And if I look at the two states which I have, I'm going now to get the following. So if I look at the qubit 0, that is simply going to give me now the following. I have 1, 0, 0, 0, 0, 1, 0, 0. And that's multiplied with a density matrix, 1, 0, 0, 1. As I said, this is not the most exciting thing, but it's actually useful to do this because it tells us how we're going to set up these matrices when we now are going to write the code. And then this is multiplied with the 1, 0, 0, 1, 0, 0, 0. And when I perform the multiplication, so this is a 2x4 matrix multiplied with a 4x4 multiplied with a 4x2. So that should give us a 2x2 matrix. And if I've done the algebra correctly here, this is 1, 0, 0, 0. And finally, what I have is the one for the bit 1. So for qubit 0 in system A, this was qubit 0. And then we take qubit 1. So that means that now we have to multiply the density matrix for the composite system A and B with this specific projection. And when we do that operation, what we will find then is that we get the final product, which is 0, 0, 0, 1. We have a component of a half. So that means that the density matrix, rho of A, which is now the trace out of system B for the composite system A and B, this is now simply given by a half times the identity matrix. And you see also that when I take the trace of this rho of A, what I get then is just a half plus a half. Because what I have then is just 1/2, and then the trace. So this is the same as, let me just rewrite this in a nicer way. This is the same as the trace of 1, 0, 0, 1, and multiplied with a factor of a half. And that gives us 1, as it should be. Now, there's another thing which is very important for us now. And that is the following. So if I look now at the density matrix, the trace of the density matrix squared for this specific subsystem. So if I take trace of rho alpha squared, this is not equal to 1. This is actually equal to a half. And it's less than 1, obviously. And this defines what we call the mixed state. And I'm going to write down what I mean by that. If, on the other hand, this trace of rho of A squared had been equal to 1, then we are going to use that to define a pure state. So we can use the trace now of a density matrix for the specific subsystem or the total density matrix. And by looking at the value of the squared density matrix, we can then define whether this belongs to a mixed state or a pure state. So a mixed state means that we cannot tell in which specific state the system was in before we perform the specific measurement. If it's a pure state, we know exactly in which state the system is in. So we are coming back to some of these definitions after the break. So I should also say one thing. In this specific case, what we are going to get is that rho of B is identical to rho of A, which again, and you can easily see that when we perform the calculations. However, if I look at rho of A of B, that is not necessarily equal to rho of A and tensor product with rho of B. So that doesn't follow immediately from these calculations here. And that's also an important property which is useful when we are setting up the total density matrices. Because if it had been, then rho of AB would just have been a tensor product of the two subsystems. And then we could define precisely in which kind of state this subsystem A is and subsystem B is. Okay, so I see that we are past the hour. After the break, I'm going to summarize what these calculations actually mean with concerning the interpretation of entanglement and the definition of a pure state. But let's take a small break here before we move on after the break with also an introduction of definition of entropies. So I'm going to wrap up this discussion about some technicalities with the tracing out of the density matrix or density operator. Now, there's a reason why we normally focus on one subsystem. The main reason for that is that, as you will see next week, many of the quantum operations which we make on a composite system, they will deal with individual qubits. So operations like this NOT gate, which we discussed some time ago, or the Pauli matrices acting on a specific many qubit state, they act on one qubit at a time. So that means that the tracing out the specific subsystem is something which is going to be important when we now are going to look at the information which we can gain by just looking at one specific subsystem. So when we have this kind of mixed state, what we can say then is the following. So the joint state, if we now limit ourselves to a system of two qubits or bipartite system, but this is something which you can easily extend to many qubits. So the joint state, so let's just write this down. So the joint state of two qubits is something which we actually, whether it's entangled or not, entangled or not, is normally known. And we would then call this for a pure state. Is a pure state. So we know in which kind of situation we started with, and it is known exactly. And it's not entangled further with an eventual environment. However, if you now look at the trace out of the individual qubits, however, looking at the individual qubits, individual, and this is actually what takes place when we are performing operations on the given systems. You could think of the system A and B, that they are well isolated and that you have confined electrons in each subsystem. And then you could act with a laser on subsystem A without affecting subsystem B, for instance. And then you would like to ask yourself, what kind of information can I gain from this type of system and operations? So when we're looking at the individual qubits of the entangled of for example, this entangled Bell state, the entangled Bell state, what we find then is we find that they are in a mixed state. In a mixed state. So we do not have, then, we do not have the full knowledge of their states. And that's essentially what this quantity we discussed before the break expresses. Now we're going to, even though these kind of definitions which we are set up now sound like very abstract definitions, this is going to turn very useful when we now are going to study explicit quantum mechanical systems. So till now, we have just dealt with some abstract concepts, and we are going to introduce another concept, which is entropy, and which is also a very useful way by which we can measure or find a measure for entanglement. And entropy is something which has played a central role, not only in physics, but also in information theory. So what I'm going to do now is actually to bring up the definition of how we can encode this information in the most efficient way. And that's going to lead us to the so-called classical Shannon entropy. So let's define entropy first. And everything is related to questions which Shannon put up. And this was back in 48, in the last century. So Shannon studied actually two questions of information theory. One was how many bits are required to reliably compress a given amount of information. That is, compress it in a way such that it can be later recovered with an arbitrary low probability of error. So that was one point. Then the other question is how much information can be reliably transmitted through a given communication channel. So what Shannon did then was to start with a definition of probabilities and think of how you can use probabilities to encode information. So if you think of one possible way of doing that is related to how can we encode this information by, for instance, giving more weight to the more unlikely events. So one of the ways of doing that is to compute the logarithm of a probability. But what Shannon did at the end was actually to calculate an expectation value as the log of the probabilities. And that leads to the definition of entropy as we know from physics. But let's now go back. So let's consider just a random variable. Which I call x. And this x is now a variable in the set of domains x, uppercase x. And it has a probability. This x has a probability with probability which we typically label as a p for the uppercase x with a specific event x here. And the information content of a specific realization of this event x, one possible way of doing that is to calculate the log, or the log in the base 2, which is pretty common since we are dealing with bits, and we have bit 0 and 1. However, you can use the log 10 base, any of these bases. And the reason for that is that the only difference is that it's just a scaling factor. So a typical way to define the information content, but this is one way of doing it. And content is something which of a specific realization of x is something which we could define as a function I of x, and that's given by minus log, and this is a log 2 of this p of x here. So why did we choose this specific function to quantify information? And there's several reasons for that. And it's easy to see that if you also make a plot. So if I plot this function here as a function of p of x, and now I'm dropping this uppercase letter x, and then we plot this I of x here, this is going to be a function which looks like this. So and this goes to 1 here, and then we have information content equal to 0, because then we have log 2 of 1, which is 0. So the information content which you have, or you might call it the information surprise, only depends on the probability of the event that the specific realization occurs, and not on the label itself. So for instance, if you have a random a variable which takes values 0 and 1 with respective probabilities 1/3 and 2/3, that should contain the same amount of information as a variable, random variable again, that takes the value of plus and minus with the same probabilities. Another thing which you also see is that this is a continuous function, which is another property which is extremely useful when we are calculating derivatives. As you can see in this figure, the function behaves exactly as we would expect from a measure of surprise. So we can call this a measure of surprise, which means that when the probability is equal to 1, we are basically in just one state. And that means that there is no surprise. But when the probability becomes smaller and smaller, then we have an element of surprise, and this function just grows up. Now, you will see that there are problems with this function when we get close to 0. And that leads also to a redefinition of this kind of information content. So the function, there's also another property. It's a non-negative function. So it's also a wanted property. It's a growing function. It's a function which has a nice mathematical properties that we'll see later when we define the entropy. The entropy is going to be a convex function. The function is additive. So we see now that if we have, suppose now that we have a probability for two events, x1 and x2 here, then we can assume now that we can write this out as two independent events. So these are independent and identically distributed events, x1 and x2 here, they have the same probability. Then we see that the information content which we have is additive. There's another property which is useful when we are looking at the information content, which means that if you take that one, you see now that this is ix of 1 and 2 here is now given by minus log 2 of px of x1 of px of x2, which is nothing but minus log 2 of p of x x1 minus log 2 of p of x of x2. And this is equal to I of x1 plus I of x2, if they are independent and identically distributed. Now, this goes back, this kind of reasoning with being non-negative, additive, contains a measure of surprise, is the a kind of answer to one of the first questions which Shannon actually asked, and that is how many bits are required to reliably compress a given amount of information. Now, it turns out, however, that this function here is not the most handy way of encoding information. And to obtain a notion for the or what is a suitable measure of information for particular realization of x of this random variable, this function which you see here doesn't capture the general amount of information that the random variable x possesses. And in order to define a function which is better suited for calculating the amount of information and just translate that one into bits, then the so-called entropy of information, or the Shannon entropy, is actually a better way of doing that. And this Shannon entropy is actually taken out as the probability times the log of the probability. So a better measure for encoding information is what is called the classical entropy, or Shannon information entropy. And this is something which we will label as an S of this whole domain of event x, and that sums over. So this looks like an expectation value, the log x, if we have discrete events. So you remember now that the quantity which we are doing now is the, if you look at the statistical definition of an expectation value, that is the function for the probability distribution multiplied with a variable which we are interested in. So the entropy is nothing but an expectation value of the log of P of x. So what we have then is the following definition of P of this total set of data points, x. This is a specific realization. And this is called the Shannon entropy. And there's also another convention which you see here, which is more handy. And we know that when the probability is 0, we know that the limit of epsilon goes to 0 of epsilon times log of 2 of epsilon is equal to 0. And mathematically then, that means that when we have 0 times log 2 of 0, or log 10 of 0, this is equal to 0. So we are on a safer ground than we were before with this information entropy, or this information content, which we put up earlier, where we didn't calculate the expectation value of log 2 P of x. So with these identifications, then we can actually answer this one of the first questions. So if we think of the Shannon entropy, it tells us that there exists a compression scheme such that the information which is being produced by the source can be stored using this function S of x, and such that information is then stored in terms of this entropy, where h now can be assigned to specific bits per source symbol. The theorem states also the so-called Shannon noiseless coding theorem, which was developed in 1948. It states also that the information, if it's compressed any further, then there is a high probability of error when retrieving the original message. So you can actually show that this is one of the most compact ways of storing information. So one of the systems which you will often see being elaborated is the case where you have a binary system. So let me just bring this up here. We have a binary system. So what we could say now is that we have two possible events. So x takes now the values of 0 and 1, only these two values. So it's a discrete set of events. And then we could simply say now that the probability of this domain of events now of getting 0 is something I will label as P. And then clearly, if I take the other one, 1, that has to be equal to 1 minus P here. And if I calculate the entropy, S of x in our case, that is going to be equal to minus P times log 2 of P. minus, and then I have 1 minus p of log 2 of 1 minus p. And then we can plot this quantity. So, and you probably have seen this before. So we plot it as a function of p from 0 to 1. And then we have 1 here. And we see now that when p is equal to half, that's when we have the maximum entropy. And it looks like this, it has this kind of bell shape. The thing which we also notice here is that when it reaches its maximum, then at 1 bit, which can be seen in a plot. So you could now see that this corresponds to 1 bit. This is the maximum entropy we can have. The other extreme correspond now to the deterministic case. Here we have p equal to 0, and here we have p equal to 1. And that case is the case where we just have one specific outcome. Whereas in the case which we have here, we have a mix of px0 and px1. So that's where we have the probability of having two specific outcomes with equal probability. When we have the probability equal to 1, then there's only one outcome which is possible. And when we have 0, then there's only one other outcome which is possible. So the entropy here reflects this kind of the information of surprise. So the deterministic states are well determined here, and that there's no surprise that this function then has to have entropy equal to 0. So this is just a way by which we now can encode information here. So the entropy function has also many mathematical properties, which are very interesting. So if I look at this S of x, it's always larger than or equal than 0, as you can also see from this simple example. And for a given specific probability distribution. So intuitively, that makes sense, because the entropy represents the number of bits we learn upon learning a specific random variable. Hence, the least amount of bits we can learn is 0, since we can never learn a negative amount of bits. And this intuition is supported mathematically by the fact that the entropy is actually the expected information content, this information content I of x, which we defined earlier, which itself is also a non-negative quantity. The entropy is also a so-called concave function. So it's a concave function. In the probability distribution, in this probability distribution P of x, which we have defined. So that means that intuitively, this implies that the entropies n increases under averaging. And you see that from the plot. It's easy to see that the binary entropy function, which we plotted here, has actually this property here. The entropy is also invariant under the permutations of different realizations of that random variable. And this follows directly from the fact that the entropy only depends on the probabilities which we can realize, and not on the realizations themselves. The entropy vanishes if x is a deterministic variable. So we have S of x, 0, when we can precisely determine which kind of state where we are in, when either P of x, this quantity P of x is equal to 1, or P of x is equal to 0. So that means that we do not have any uncertainty in the outcome here. There's no uncertainty. And that's why we put the entropy equal to 0. There's no uncertainty about a deterministic variable. You know that you are exactly in that specific state. There's nothing undetermined here. No uncertainty about deterministic variables. So what I'm dealing with now is still a classical entropy. when we come to quantum mechanics, we will have to change a little bit here. And there are also some surprises which come into play here. And the other thing is that if we have a given random variable that takes the values in this quantity x, what you can also show is that the entropy, so that's the next property, this entropy S of x is actually larger than equal than log of this specific variable x here, which we have. So where this parenthesis is the cardinality of this kind of set of events which we have. And this equality holds only if x is a uniform random variable. Now, the entropy itself, when we now go into quantum mechanical discussions, has to be modified a little bit. You can, however, before we move into the quantum mechanical aspects, you can make many other statements about conditional entropies. You can look at marginal entropies, which relate to marginal probabilities, etc., etc. But we are not going to discuss all these quantities. What we are going to be interested in now is actually the quantum mechanical entropy here. So let's go to quantum entropies. And this is where the density matrix is going to play an important role. So what we are going to look for now is a quantity which is called the von Neumann entropy. So this von Neumann entropy, which we're also just going to call for just the quantum entropy, is a generalization of the Shannon entropy, the classical one, to quantum system. So it's a generalization. Generalization of the Shannon entropy to quantum systems. And the unit of information that we now use to determine the amount of quantum information is going to be a system of quantum bits. So that means that the unit of information is going to be quantum bits. And the what you have to recall also when we're looking at this discussion is that the classical entropy, which we discussed, is a direct function of the probability distribution of a random variable. So it captures, in a certain sense, what you might call the classical uncertainty, or what we call this element of surprise, which we would have about a given system. Now, in the quantum world, the classical uncertainty about a system, as well as quantum uncertainties, which obviously arises from the uncertainty principle, is actually captured by this density operator. So that means that we can make a quantum analog of the Shannon entropy to be a direct function of the density operator. And if we do that, this is going to have some interesting properties, which is going to allow us to calculate this entropy in a very straightforward manner. So let's now look at the definition of the quantum entropy. So keep in mind, as we have seen now with this density operator, the density operator is actually a quantity which is given by the spectral decomposition of this density operator, where the eigenvalues play the same role as probabilities of the density matrix. And you could then say that the quantum uncertainty, which comes from the uncertainty principle, is in a way captured by this density matrix density operator. So that means that if we now look at the definition here, so we can let A be a quantum system, that is prepared in a state which we call for rho alpha. So this state rho alpha is actually, as we discussed earlier, due to the Schmidt decomposition. So just reminder here, hint, this goes back to the Schmidt decomposition. So we have defined this state, which is now a member of the Hilbert space A. So it belongs to this specific Hilbert space. Then the von Neumann entropy is defined as follows. Entropy is defined as this S of this rho of A, or just A, and that's given as the trace of rho of A multiplied with a log, and now I leave it undefined whether it's a log 2 base or another base. This just introduces a scaling factor. So this is the definition of the von Neumann entropy, and the quantity now which is useful for us, if you think back of the spectral decomposition of this specific state, or the spectral decomposition of the density matrix. So the spectral decomposition is now given by this quantity here, where we sum over all these specific states. So that means that we have a sum over J of lambda J, and then we have the states psi of J of A and psi of J. And these lambda i's are the eigenvalues of the density matrix. And so lambda j's are the eigenvalues, and they are interpreted as probabilities. As we've seen, these are the probabilities. And this phi of J of A, they are the corresponding orthogonal and normalized eigenvectors, are the corresponding eigenvectors. Orthogonal eigenvectors. So what I've used there is actually the spectral decomposition, which we introduced 2 or 3 weeks ago. So this quantity here is something which we can actually rewrite in a very handy way, and then it's going to look like the standard Shannon entropy. So in order to see that, let's now show the following. So let me just find my notes here again. I just need to figure out where I placed it in my notes. So if you now think of the density matrix, so this quantity rho of alpha, one of the things which we have said is that this is a semi-positive definite quantity. It's a semi-positive matrix, which means that it has eigenvalues larger or equal than 0. It also represents a convex, it's a convex quantity. We know that since this is a semi-positive definite matrix, definite matrix, it means that it's always diagonalizable, and is always. So we can always find the eigenvalues for this specific matrix. This is by construction, and you've seen the cases which we have calculated earlier. This is a matrix which we can actually, when we compute the final density matrix, we can always diagonalize it. So that means the following, that there is a unitary transformation where we now can transform this matrix. So we can take the matrix rho alpha, and this can now be transformed by a unitary transformation of rho of A prime of U. And where actually this matrix here is a diagonal matrix. This is a standard way by which we actually calculate the eigenvalues and eigenvectors of a specific matrix, where U now is a matrix which is given by, this is a unitary matrix, where the inverse is the self-adjoint of the matrix. And that means the following, that if I now calculate the following quantity, what I get then is that I have that U of minus 1, or the inverse, times rho of A. And then what I'm looking at now is log of rho of A, and then multiply with U here. So I'm multiplying with U of minus 1 and multiplying with U on the other side. So this quantity here, if I can now insert just the identity, which is U times U minus 1, then what I have, if this matrix now diagonalizes the matrix, then this is going to give us a D of A. And then I'm going to define, and you can actually show that if I take the same unitary operation on the log of rho of A times U, you can actually rewrite this as a log of D of A, so the diagonal elements only. Now, there's another statement as well, which is important, and that is that, and I'm just stating this, as a log D of A is now given by the following. It's given by the log of lambda, the first eigenvalue, and down all the way to the final eigenvalue of lambda of n minus 1. So this is a matrix of dimensionality n times n, and you can actually rewrite it like this. So that means again that if I then calculate the trace of these matrices, and then I know that the trace of D of A is just the same as the sum over the eigenvalues of the matrix, I equals 0 up to n minus 1 in lambda of A here. If I take the trace of this matrix, D of A of log D of A, so I'm just stating this result here, and you can find this result in the textbooks on linear algebra, advanced textbooks on linear algebra. If I take the trace here, this is simply going to be given by the trace, or just the sum. So it's going to be a sum over the eigenvalues of lambda y, and then I have log of lambda of I. So remember now that the trace of a diagonal matrix is just the sum over the diagonal matrix elements. So this is now a product of two matrices, and log D of A is just a diagonal matrix. D of A is a diagonal matrix. So that means that my final product is just the log, the sum over the logs times the of the eigenvalue times the eigenvalues. So the trick here is actually to use the unitary transformations in order to show this relation. And lambda I represents a probability. So that means that if I now look at the definition which I had of this sigma, this quantum entropy, which I define as an S of A. So let me just rewrite it as an S of A here, which I wrote as minus, and then I had the trace of the density matrix times log of the density matrix. This is something which I now can rewrite as minus, and then I have a sum of lambda i's of log of lambda y's. And these lambda i's, they are probabilities when I look at the spectral decomposition of the density matrix. So that means the following: if I go back to the Shannon entropy, we have a quantum mechanical equivalent of the Shannon entropy, but which is now given in terms of the probabilities, which are the eigenvalues of the density matrix. And the Shannon entropy, which was defined as this X, was simply the sum over all the possible realizations of this probability. So let's now write this as an X here, which is the whole domain of events of X times log of P, the whole domain of events, where we picked out one specific little x event. So the Shannon entropy is the classical entropy. And now you see that we have a quantum mechanical equivalent to the Shannon entropy. And the mathematical properties of these matrix here is basically the same as we had for the other one. So this S of A is larger than or equal than 0, which we can see immediately. And the entropy vanishes if and only if the density operator is a pure state. So we can put this one. So we have S of A is equal to 0 if the density matrix is given by pure state. Is a pure state. So that's also a very useful way to define whether we have a pure state or not, by simply calculating the eigenvalues of the density matrix. And then when we have the eigenvalues of the density matrix, we can compute the von Neumann entropy, and this vanishes, the entropy vanishes, if and only we can determine the state exactly. We would then say that the outcome which we have is a deterministic variable. We know exactly in which state the system is. If it's a mixed state, then the Shannon entropy, the von Neumann entropy is going to be non-zero here. So the other property is that the maximum value of the entropy is actually given by the dimension of it's smaller than the dimension of or equal to the log of the dimension of the system. And the entropy itself is invariant under unitary operations, which we can see immediately. And we're going to bring up some of these topics next week when we summarize the entropy. So I was hoping that I would be able to get into the example which we have, but it seems that we will need some time next week to actually discuss that specific example with a 2-qubit system and how we can extract, one, the subtrace of the density matrix and use that one to say something about entanglement or not, whether we are in a mixed state or pure state. And the other thing which we're going to compute next time is this von Neumann entropy from this system of 2 qubits which may interact with each other. So I'm going to stop here because these quantities which we have defined, everything till now has been what we might call background material, but we are going to need this background material when we now are going to analyze quantum mechanical systems, and when we are going to set up quantum circuits and quantum gates and perform measurements on a specific quantum mechanical system. And these measurements, just keep that in mind, these measurements are made typically on individual qubits, which means that the quantities like this subsystem density matrix are going to play a very important role. And the same happens when we now are going to analyze the data in terms of these entropies and how much information is encoded in a specific state, because that's going to tell us something about whether the states are pure states or not, or mixed states. So you may not see the the wood for the trees yet, because we have just brought in many definitions, but hopefully when we now are going to implement these things, both in terms of simple quantum algorithms, but also into simulations of more, how to say, realistic Hamiltonian systems, then you're going to see the importance of these quantities here. So next week, we will start with the example which you'll find in the slides. And that example there gives you some basic intuition on how to build up the subtraces and how to compute the von Neumann entropy, which we then later will use in the analysis of different systems. But this concludes today's lecture. Some